Welcome to lecture 34. In this lecture, I will set up the quantum field theory for gauge fields. So far, we've dealt with quantum field theories for scalar fields and for fermions. An important class of quantum fields that we have not talked about, but that are found in nature, are gauge fields. In this lecture, we will start our discussion on how to set up such gauge field quantum field theories. To get started, recall that in lecture 22, we discussed the action for a complex scalar field that is given in equation 34.1. We found that in addition to Lorentz invariance, the action SE given in this equation is also invariant under transformation phi goes to e to the I alpha phi, where alpha is an arbitrary constant. Because alpha is a constant and as such does not depend on space or time, we call this a global U1 transformation. The action that we had just had on the previous slide is invariant under this global U1 transformation. We also have a different name for this global U1 transformation. We call it a gauge transformation because we changed the field phi, so we are re-gauging what it means to have a certain value of phi. If we make alpha dependent on space or time, or both, the generalization of the global U1 transformation is called a local gauge transformation. Phi goes to the e I alpha of x, phi of x. We found that the action is not invariant under the local gauge transformation. It is invariant up to linear order, but it's not invariant under the transformation that's given in 34.3. However, we can try to change the action such that we find a theory that actually is invariant under such a local gauge transformation. Let's have a look at this in detail. If we plug in the transformation, phi goes to e to the I alpha of x phi, then the derivative of phi gives rise to a term that is e to the I alpha of x phi times the derivative of phi. That's the term we would expect, and that's the same as with a local gauge transformation. But in addition, because alpha now also depends on x, there's a second term that is proportional to the derivative of alpha that we get in the gauge transformation from the derivative of phi. We can nevertheless ask ourselves of how we can modify the action in order to make such an offending term go away. One such possibility is that we add a new field to the action. We call the field A, and it has a vector component, index A, such that we write the action in terms of the derivative of phi, but we add the new vector field A in the derivative in such a form here, such that the total form of the action is still real. And if we, in addition, require the field A to transform in the following way, so that under the gauge transformation, A goes to A minus the derivative of alpha, and we use the same gauge transformation for the field phi, we find that the combination of these two transformations is such that the offending term in the derivatives just cancels, and the resulting action is now invariant under the local gauge transformations. It is useful to define a new name or notation for the combination dA minus IA, and we call this capital D, where capital D is now the gauge covariant derivative, or covariant derivative for short. Using this notation, we can write the action as an integral over space time x times the covariant derivative of phi times the covariant derivative of phi complex conjugate. And of course, we can have our potential that is still an arbitrary function of the square root of phi and phi star. Such an action is manifestly real, it's Lorentz invariant, and it also is invariant under local gauge transformation. We call the new field that we've introduced, this vector field A, the local U1 gauge field. Since we have a new field, we may ask if there are now additional terms that have these properties of the action, which means that they are real, Lorentz invariant, and invariant under the local gauge transformation. The answer to this question is affirmative. There are such terms. And in particular, if we consider an antisymmetric tensor FAB that's built in the following form, so it's the derivative of AB minus the derivative of AA, then this particular combination is a Lorentz tensor. And it's straightforward that this tensor is also invariant under local gauge transformations because it's antisymmetric. So the derivative for this first, coming from the gauge transformation of this first term, will cancel exactly against the derivative of the gauge transformation of the second term. We call FAB the field strength tensor, and we can add a piece to the action that involves this field strength tensor in the following way. So we can add to our action that we had before a term that's FAB times a constant, but the constant is conventionally fixed to 1/4. Since this additional term that we've included here is also real, invariant under Lorentz transformation and invariant under gauge transformations, that means that the total action has the same properties. Note that there would be another possible contribution that we could write down. This you can build out of the field strength tensor FAB times the so-called dual field strength tensor, which is FAB times epsilon ABCD. So this combination here is the epsilon here is the 4-dimensional Levi-Civita symbol that's totally antisymmetric in its indices. This term would have all these same properties here, but it has the property that it violates another symmetry, namely parity, which we would like to have. I have not talked about this, but this action written in equation 34.10 is also invariant under parity. If we would include a term like this, we would break parity. For the time being, I'd like to keep this additional symmetry, and for this reason, I will forbid the contribution from FF dual that we could in principle also include in the action. The action that is written in equation 34.10 defines a theory that is called scalar electrodynamics. Why is it called that? It's called that because the equations of motion for the gauge field A are nothing but the classical Maxwell equations. The gauge field is coupled to the complex scalar field via the gauge covariant coupling. And that means that the coupling of the gauge field to that other field, the scalar field, means that the complex scalar field corresponds to the so-called matter content of the theory. Simply put, the scalar field phi is equivalent to the electron field in real electromagnetism. The electron field in quantum field theory would be a fermionic field because it's spin 1/2. Scalar electromagnetism is not a real theory as realized in nature. It's a toy theory, and as such, it is a little simpler to treat than the real thing, but it carries many properties of real electromagnetism, which we would like to discuss in the following. So far, all of our discussion has been done on the classical level of the action. We could try to do a quantum field theory of scalar electrodynamics by just writing down a path integral for the partition function, such as this. So integral, or z being path integral over the scalar fields phi star phi, and a path integral over the new field A that we included times e to the minus SE, where SE is the classical action that's given in equation 34.10. It turns out that if we just write down this expression here, we will encounter difficulties that were not present when we were doing or when using the same approach for scalar fields and fermions. We will discuss these difficulties and their real solution in the following lectures. And this concludes the present lecture.